Now we go for the next device, which has got the 3 doped region, 3 doped segment. Rather, earlier there were 2. Now we have got the 3 doped segment, and such a device which has got the 3 different doped region we call junction transistor, या bipolar junction transistor. In the short form, it is also known as an BJT. Now, what is junction transistor? This junction transistor has got the 3 doped region. Depending upon the arrangement of these doped region, the position of these doped region, we have 2 type of the transistor. One is PNP transistor. In the PNP transistor, in between the 2 doped P region, we have a thin layer of N region. Between the 2P region, a thin layer of the N region is placed, developed, then such a device we call PNP transistor or PNP junction. Another one is like the same NPN junction transistor. Here between the 2 N-type semiconductors or 2 N-type doped region, we develop a very thin P region. Then such an arrangement, such a device we call NPN transistor. Now what is the difference? What is the major importance part of this? In NPN or in PNP, either of them, one of the doped region at the end is heavily doped. This is a heavily doped region, and it works as a source of the charge carrier, and it's called emitter. It is not big in size, it's a moderate of the size. Another similar region, like region at the other end, like P this side, the P other side, N this side, and other side. This region is lightly doped, and it is moderately doped and has got the large area. Surface area is large. It acts as a collector of the charge. So we call this collector. So we have the one region at the one end, heavily doped, act as a source of the charge, emitter. Another similar region, similarly doped region, which is moderately doped but has got the large area. Its purpose is to collect the charge, is called collector. So emitter and collector. And the sandwich region, the region in between the two, which is very thin in the thickness, and very lightly doped, and which is of the opposite kind. Its work is to regulate the flow of the charge which go from emitter to collector, because they have to pass through this region, and this is called base. This is called base. So this way the transistor has got the 3 region, different level of the doping, different level of the thickness also. One is emitter, heavily doped, one is collector, moderately doped, and one is sandwich region is base, which is very lightly doped. The difference in the PNP and NPN is that in the PNP, the current will be because of the flow of the hole, because emitter will be source of the hole. So current will be because of the flow of the hole. And in the NPN, because emitter is an N-type semiconductor, which is the source of the electron, where the majority charge are electron. So here the current will be because of the flow of the electron. So in the PNP, the current will flow from emitter to base, while in the NPN, the current will be, direction of the current will be from base to emitter, because electrons are going from emitter to base, right? Now how we make a symbol of it? Like we have got the symbol for PN junction, similarly we have the symbol for NPN junction and PNP junction transistor too. Here we make the symbol by, in a circle, we have like this. Two lines on the table like structure here, and similar in this one within a circle, one of the line has got the arrow inward. The line on which we mark an arrow is an emitter. The table type, T type of the things we call the base. And the other one line without arrow is called the collector. This is PNP. How we can identify it as a PNP? The direction of the arrow. It is from emitter to base. I told you in the PNP, P is source of the hole. So direction of the current will be P to N, emitter to base. In the NPN type semiconductor, NPN type transistor, we have the symbol same as that of the PNP. The only thing is that this time the emitter, on the emitter line, the arrow is marked upward, outward from base to emitter, right? Why it is marked outward? Because in the NPN, what are the majority charge carrier flowing from N to emitter to base? It is the electron. So direction of the current will be opposite, base to emitter, base to emitter. Current direction is base to emitter. Electron flow will be emitter to base. So arrow is marked upward. So this is the symbol of transistor, emitter, base, collector, the three terminal device it is. As I told you that we have got the two PN junction over here. One is between the emitter and the base. Another is between base and the collector. So first we have to connect the battery between the first emitter base PN junction. It is between emitter and base in order to push the electron from emitter to base. For this, we'll connect the emitter, which is N this time, with the negative of the battery and P with the positive of the battery. Now, N is negative, P is positive. This biasing we call the base biasing, and this is forward bias. How it is forward bias? Because N is negative and P is positive. What this forward bias will do? It will push the electron from N region to P region. So electrons are being pushed from N to P, and they will constitute, these electrons as they move from N to P, they will constitute then emitter current in the circuit. Now, when these electrons reach to the base region, we are required them to collect at the collector. Again, we'll have to connect another one battery across base and collector. Now this time, because you require to collect electron at the collector, so collector terminal must be positive and the base terminal must be negative. This is the collector biasing with the N negative, positive and P negative. Now what type of the biasing it is there? N negative, P positive, it is a reverse bias. So what happens when you make this reverse bias, the N positive, these electrons will reach at the base region. Some of them will get neutralized. Few, very few, because base region is very thin. Say out of 100 from the whole, few electrons are neutralized, and remaining electron, say 95% of them, they reach to the collector region and they constitute the collector current. They constitute the collector current. Direction is upward, because electrons are flowing here. Direction of the current is this way. So electron when they reach, here the current is outward. So the electron when they reach to the collector region, they constitute the collector current. Electron when they leave from the emitter region, they make the emitter current. And few of those electrons which get neutralized in the base region, for them to compensate them, few more electron comes, equal amount of the electron come from the cell, and that will make the base current. Base current will be very small, only 5% of the emitter current. Why? Because very few of the electron get neutralized. About 95% of the electron reach to the collector region. So for the junction to conduct, emitter base junction should be forward bias. Base collector junction should be reverse bias. By using the Kirchhoff law, the emitter current will be equal to the base current plus collector current. Base current will be about 5% of the emitter current because only few holes are there to neutralize the electron. Collector current is about 95% of the emitter current because many of these electrons reach over the collector region, and then this PN junction become, or this junction transistor become conducting operative, right? So two battery, one in forward bias, one in reverse bias, emitter forward bias, collector reverse bias are necessary for making the transistor or PNP or NPN junction operative. I have done it for N-type semiconductor. You can also try connecting the battery with the same PNP type of the transistor. The only thing is that wherever is the emitter, it should be forward bias. If it's a emitter is P, it should be positive. If emitter is N, it should be negative, right? So this is biasing of the PN junction. I told you that transistor is 3-terminal device. It has got the, suppose if we take the NPN, one is emitter, one is base, another one terminal is collector. For any device to connect, we require the 4 terminal, 2 for input and 2 for output. So what we do, in order to make it as a 4-terminal device, a 2-port device, we make one of the terminal as a common. When we say common, we mean it can be used in both sides. Or we can say we make the one of the terminal as a grounded. So depending upon which terminal is grounded or which terminal is made common, we have the 3 type of the arrangement, circuit arrangement for the transistor, which can be used for the various purpose. The first configuration is common base circuit, common base, yeah, grounded base. Here we make the base common. Now how we make the base common? What's the circuit arrangement? This is our transistor. Here is an emitter. I make it NPN, current is moving outward. This is an emitter. This is base. This is collector. And I make the base common to emitter and base common to collector. This is common base device. Here, this side is input between emitter and the base. This side is output between collector and the base. Input current will be the emitter current. Output current will be the collector current. Input voltage will be emitter base voltage. Output voltage will be collector base voltage. Base current will ignore because it is grounded, right? So this is common base circuit with the input current, input between base and emitter, output between collector and the base. Input current is emitter current, output current is collector current. Input voltage is emitter base voltage, output voltage is collector base voltage. This is common base circuit. Second one is, the second one we take common emitter circuit. Common emitter, we slightly modified the arrangement. Here we make the transistor like this. We arrange it this way, emitter downward, collector here, and base this side, collector toward the right side, and emitter is made common to both of them. Input is between base and emitter, output is between collector and emitter. Here this side is input, this side is output. Input is between base and emitter, output is between collector and emitter. Now this time input current will be the base current, IB. Output current will be the collector current, IO will be IC, because emitter current will be grounded. Input voltage will be I, V, B, E, and output voltage will be V, C, E. Here, compared to the common base, this circuit is more advantage. In case of this circuit, emitter current, input current is 100% and output current is 95%. Out of 100% that we give in input, we get the 95% output. When we use this type of the circuit with the common emitter, input current is a base current, which is 5% of the input emitter. Output current is a collector current, which is 95% of the emitter. So we give 5% of input and we get 95% of output. So this circuit is very, very useful circuit and most commonly used circuit. The third circuit is common collector. Third circuit, common collector. In this case, as you observe, we have made the collector common. Collector between the emitter and the base, emitter and the collector input, and output is between base and collector. So collector is made common with both emitter and the base. We call common collector. It is very rarely used circuit. Why it is rarely used circuit? You see input current is emitter current. This side is input. Output current is base current. So with the 100% of the input, you get only 5% of output. So this circuit is very, very rarely used circuit, right? Because we get very less output with the large input current, right? Now we come to the characteristic of the PNP or NPN junction transistor. Characteristic, as I told you that we have done it in the PN junction. Characteristic means the graph showing the variation of current with the voltage, applied voltage. Now here in case of the transistor circuit, we have the two voltage. One is between emitter and base, another is between collector and the base, or like we say one in input, another is in output. And two current also, input current and output current. So in the transistor circuit, we have the two main characteristic. One we call input characteristic, another one we call output characteristic. But before drawing the characteristic, the graphical variation between current and the voltage, we have to make an arrangement for the circuit. How we arrange the circuit? Let us take the common emitter configuration, which is most useful circuit. First we make the transistor common emitter configuration. This is base, this is collector, this is emitter. Say I make PNP. How you know that it is PNP? Arrow going inward from emitter to base, it is PNP. This side is PNP. This is common emitter configuration. Now we connect the battery in both sides, input side and output side. This is PNP, this is emitter, this is base, this is collector, this is P, this is N, this is P, PNP. Now I told you that emitter must always be forward bias. So when you connect this emitter, it must be connected with the battery, positive to the P and negative to the N. This is base biasing voltage and we measure it by a voltmeter. This is base emitter voltage it is reading. This is the base biasing, which is biasing the emitter in the forward way, forward direction. This is the forward biasing. Here is to measure the voltage, we use a voltmeter which is reading the things. We use an emitter here, is a micro emitter, mu A. because it is recording the base current. So we use a microammeter to record the base current, input current. Now let's come to the output. Output is collector. I told you that in the transistor circuit, the collector must be reverse bias. And what type of the semiconductor the collector is? It is a P-type. So it must be reverse bias. So our battery must be connected in such a way that P must be negative. In the reverse bias, P negative and N positive. Negative. This arrow shows is a variable voltage. This is the collector biasing voltage. It is reverse bias. To measure this output voltage, how much we are changing the voltage, we use a voltmeter which will record the base collector emitter voltage, and we'll use an ammeter, milliammeter over here, which will measure the collector current. This is input side. This is output side. So input current is base current and input voltage is base ammeter voltage. This is output side. Output current is a collector current and output voltage is collector ammeter voltage. Now we use the two characteristics. In the one graph we show how the input current varies with the input voltage. In the second graph we show how the output current varies with the output voltage. First characteristic is input characteristic. It is input current versus input voltage. In this case of the common ammeter, it is base current versus base ammeter voltage at constant output voltage at constant collector ammeter voltage. Now, so input characteristic is between input current and input voltage at constant output voltage. Since input junction is forward bias, it is forward bias. So characteristic will be the same as forward bias PN junction. Here we take input voltage which is VBE. Here we take input current that is IB. The graph will go this way. At constant output voltage V1, if we increase the voltage, it will be a little bit more, and if we further increase the output voltage, it will be a little bit more. So at different output voltage, we have got the just similar graph, same as that of the forward bias PN junction. Slope will be the input resistance delta IB upon delta VBE. So input resistance will be delta VBE upon delta IB, which is very, very small. I told you in the forward biasing, resistance is small because more current flow, large current flow. With a very small change in the input voltage, it causes a large change in the input current. Now we'll be taking the output characteristic. Output characteristic is between output current versus output voltage. That shows the variation of output current with output voltage. Now in this our common ammeter circuit, if you remember, if you go through the circuit, you'll find that output current is collector current and output voltage is collector ammeter voltage. Now here when we draw this characteristic, we keep the input current constant. In the circuit of the common ammeter, input current is IB. So we keep the IB constant. So our circuit is IC versus VCE at constant IB. Now what type of the graph will be there? It's just to remember the graph. Remember that output is always reverse bias. I told you the collector is always reverse bias, ammeter is always forward bias. So output is reverse bias, so output characteristic will be same as reverse bias PN junction. You know the characteristic of the reverse bias PN junction. I just again remind you, it is a forward bias, voltage versus current. And this is the reverse bias, constant leakage current flow. We call the reverse saturation current, which is not changing much with the voltage. So our graph output characteristic will be this one portion. It will be like this one portion. So here also we have the output voltage on the x-axis, output current on the y-axis. Output current is a collector current, so it is to be measured in milliampere. Output voltage is in volt, and base current, that is input current, we are keeping constant. So first we draw the graph, and what we observe, that with the increase of the voltage, the current is increasing, output current is increasing very rapidly initially, and then become almost constant at constant IB. Then we change the IB again, we change it say from 0 to 10 microampere. We find that current is again increasing initially, very slight change in the voltage, it increases rapidly, and then again it becomes constant. Then this way what we observe, with change IC is changing only with the change of IB. Otherwise, for the larger change of the voltage, it is almost constant. It's not changing much. If you take 40, it has changed initially a little bit, very rapid change, and then almost become constant. So what we observe, it is constant for the larger change of the bigger change of the output voltage. Initially, it increases with the increase of voltage, right? So this curve is similar to that of the output of reverse bias of PN junction. From the slope, we can get the output resistance, slope of this output characteristic, and output resistance will be, we can draw the output resistance. Output resistance will be change in output voltage upon change in output current. Because it is a change in output voltage, so it is sometimes also referred as a dynamic resistance or AC resistance. This resistance is very large, because output current changes only in a microampere. The value of this resistance is very, very large. So we observe output resistance is very, very larger than input resistance.